Hello everyone, we will discuss the basics of radio frequency in this lesson. Let's take a look at our topics. In this course, we will discuss topics such as radio frequency overview, understanding frequency, wireless band and channels, what is decibel, how to transport data over an RF signal. First, let's give an overview of radio frequencies. To send data over a wired connection, electricity is applied to one end and transported to the other. The signal can be easily transmitted because the wire of the cable is continuously conductive, but a wireless connection does not have any physical way to carry the signal, so how can an electrical signal be sent in the air or in an empty space? Let's imagine that two people who are standing far away from each other are tied to each other with a rope, where the rope represents empty space. The sender lifts up the end of the rope and holds it there. The rope goes down after a short distance, and the receiver does not notice any changes. As shown here in Figure 1, the sender lifts the rope up and lowers it down after a certain period of time, and nothing reaches the recipient. The sender cannot push the rope, but when he starts to shake the rope up and down with a continuous and regular movement, a continuous wave pattern appears along the entire length of the rope, as shown in Figure 2. In fact, these waves go from the sender to the receiver. Figure 2 shows an example of this, where when the sender starts to shake the rope up and down, the waves reach the receiver in this way, and a similar process occurs in empty space, that is, in the air. The transmitter can send an alternating current with the antenna, creating the moving electric and magnetic fields that propagate out and away as moving waves. The electric and magnetic fields move together and always move at right angles to each other, as shown in Figure 3. To keep the electric and magnetic fields spinning and pushing outwards, the signal must continue to change, rotating upwards and downwards. Electromagnetic waves do not travel in a straight line, but instead travel away from the antenna by expanding in all directions. The resulting waves start small and expand outwards, only to be replaced by new waves. In empty space, electromagnetic waves expand outward in all three dimensions. Here he shows a simple antenna. The waves produced expand outward circularly, and the waves reach many positions and receivers in other directions. On this page, let's examine the radio frequencies in a little more detail. The waves in a wireless connection can be measured and defined in various ways. One of the main characteristics of the wave is the frequency of the wave, or the number of times the signal completes the up and down cycle every 1 second. Figure 5 also shows how the cycle of a wave occurs. A cycle can begin when the signal rises from the center line and falls from the center line and rises again to meet the center line. It can be measured as a loop from the center of one peak to the center of the next peak. No matter where you start measuring a cycle, the signal should be in complete order to the starting position, where it is ready to repeat the same cyclic pattern. Suppose 1 second passes, as shown in Figure 5. During this 1 second the signal travels through 4 full cycles, so the frequency is 4 cycles in 1 second. 4 Hz. Hertz, the most commonly used unit of frequency, Hertz, represents the cycle that occurs in 1 second. To simplify things, as the numbers can be quite large as the frequency increases by order of magnitude, the names of the frequencies can be changed to point to an increasing number of zeros, as listed in Table 1 below. Here we can define 1000 Hz as 1 kHz, 1 million Hz as 1 MHz, 1 billion Hz as 1 GHz. Here, Figure 6 shows a simple representation of the continuous frequency spectrum ranging from 0 Hz to 10 over 22 or 1, or then to 22.0 Hz. At the bottom of the list are the frequencies too low for the human ear to hear, and then the sounds it can hear, the highest frequency range of which indicates X-ray, gamma, and cosmic rays. The frequency range from about 3 kHz to 300 GHz is often called radio frequency. This frequency range includes many types of communication, such as low-frequency AM radio, shortwave radio, television, FM radio, microwave, and radar. The microwave category also includes the two main frequency ranges used for wireless networking. Multiple frequencies can be used for the same purpose. For example, the range of 530 kHz to about 1710 kHz is used by AM radio stations, so they are often referred to as the AM band. One of the two frequency ranges used for wireless networking is between 2400 and 2485 GHz. Although it does not cover the entire range, between 2.4 and 2.5 GHz, we usually refer to it as the 2.4 GHz band because it is much easier to refer to the band name instead of the specific frequency range included. On this page, let's talk about the wireless band and its channels. One of the two frequency ranges used for wireless networking is between 2400 and 2485 GHz. Although it does not cover the entire range, between 2.4 and 2.5 GHz, we usually call it the 2.4 GHz band. Those in the range of other wireless networks are also often called the 5 GHz band, because they are between 5,150 and 5,825 GHz. The 5 GHz band actually includes the following 4 separate bands. Our first band, UNI-1, is used between 5,150 and 5,250 GHz, while UNI-2 is used between 5,250 and 5,350 GHz. UNI-2 Extended is used between 5,470 and 5,725 GHz, while UNI-3 is used between 5,725 and 5,825 GHz. A frequency band contains a continuous frequency range. What frequency can they use if a single frequency is required for wireless communication between two devices, and how many unique frequencies can be used in a band? To keep everything organized and harmonious, bands are usually divided into several different channels. Each channel is known by a channel number and assigned to a specific frequency. These channels can be used consistently in all locations as long as they are defined by bodies that set national and international standards. Figure 7 shows the channel layout for the 2.4 GHz bands and Figure 8 shows the channel layout for the 5 GHz bands. Here 2.4 GHz also shows the channels we use. We have channels from 1 to 14. In the 2.4 GHz band our channels 1, 6 and 11 broadcast without conflict, and in 5 GHz we have 23 non-overlapping channels, so these channels are more widely used today. On this page, let's talk about decibel. The concept of decibel appears in many areas such as acoustic electronic antennas, optical systems, and signaling. Decibel is a logarithmic unit used to measure the sound level and express the ratio of two physical values. These compared values can be values such as sound voltage, electromagnetic wave intensity, and so on. The decibel is associated with a 10-based logarithm. 1 Bell decibel is 10 decibels. This unit is attributed in honor of Alexander Graham Bell, but this unit is not used much. The definition of decibel was defined in the United States in the early 20th century when the Bell Company made telephone power measurements. Today this unit is widely used in many fields of science and engineering. These areas can be listed as control theory, electronics, acoustics and so on, while the gain or loss of electronic signals and noise is mostly expressed in decibels. Now let's look at the decibel types. There are many types of decibels, but we use decibel types like dBm, dBi, dBd in our wireless networks, so I'm only going to talk about these 3. dBm is a type of electronic acoustics. dBm has a relative value of 1 milliwatt. For sound and telephones this value is usually taken relative to the impedance of 600 ohms, while for radios the calculation is made over 50 ohms. dBi and dBd are antenna measurement types, where I stands for isotropic. dBi, isotropic is used in calculations where an antenna receives or transmits equal energy in all directions, often used to express the gain of an antenna. dBi measures how much an antenna increases the effective signal strength. dBd is 0 dBd equal to 2.15 dBi if we compare between high-gain antennas and half-wave. On this page, let's look at transporting data over an RF signal. So far we have only talked about the radio frequency characteristics of wireless signals. The radio frequency signals presented have only existed as simple oscillations in the form of sine waves. The constant and predictable frequency is important because a receiver needs to be tuned to a known frequency in order to find the signal in the first place. This basic radio frequency signal is called a carrier signal because it is used to carry useful information. Audio signals are transmitted via AM and FM radio carrier signals, while TV carrier signals carry both audio and video signals. Wireless network carrier signals also need to carry data. The frequency of the original carrier signal must be maintained to add data to the radio frequency signal. For him, there must be a scheme for changing some properties of the carrier signal to distinguish between the bits 1 and 0. Regardless of the schema used by the transmitter, it must also be used by the receiver so that the data bits can be interpreted correctly. Wireless networks need to carry data at high bit rates that require more bandwidth for modulation. As a result, the data sent is spread over a range of frequencies, also known as spread spectrum. Wireless networks at the physical layer can be divided into 3 spectrum categories. The first is known as frequency hopping spread spectrum FHSS, the second is known as DSSS, and the third is known as orthogonal frequency division multiplexing OFDM. OFDM is the most used spectrum model today. Let's look at FHSS first. FHSS is no longer used today, but I will talk about it in terms of your knowledge when it comes up. Figure 9 shows an example of how the FHSS technique works, where sorting starts at channel 2 and then moves through a designated sequence to channels 25, 64, 10, and then 45 and so on before repeating, and jumping between channels must be done at regular intervals so that the transmitter and receiver remain in sync. In addition, the receiver must calculate the jump order in advance so that it can set the correct frequency at any given time. On this page, let's look at DSSS. The direct sequential spread spectrum uses a small number of wide channels that can support complex modulation schemes and scalable data rates. Each channel is 22 MHz wide and supports speeds of 11 megabits per second. In the 2.4 GHz band that it uses, there are 14 possible channels, but only 3 of them do not overlap. In this way, you can also see channels that do not overlap. Channels 1, 6, and 11 do not overlap. If we use other channels, there may be conflicts. Let's look at OFDM. DSSS emits a single data stream over a wide 22 MHz channel. It is inherently limited to 11 megabits per second data rate due to the consistent 11 MHz chip speed that feeds RF modulation. OFDM sends bits of data in parallel over multiple frequencies located on a single 20 MHz channel. Each channel is divided into 64 subcarriers in the 312.5 kHz range, with subcarriers also divided into the following types. It is divided into guard, pilot, and data. Guard, it uses 12 subcarriers to help distinguish one channel from another and to help lock receivers into the channel. The pilot is placed in equal spacing with 4 subcarriers and is always transmitted to help the receivers assess the noise status of the channel. Data is dedicated to carrying data with 48 carriers. Figure 11 shows an example of OFDM where channel 6 in the 2.4 band is 20 MHz wide with 48 data subcarriers. OFDM is named because of the way it takes a channel and separates a number of different frequencies for its subcarriers. Note that the subcarriers are placed very close to each other and overlap. The overlapping parts are aligned in such a way that they eliminate most of the potential interference. OFDM encoding has sprinkling and modulating functions, but it gains its scalability by using so many data subcarriers in parallel, although the data rates from each subcarrier are relatively small, resulting in a high data rate of some of all subcarriers. The table here shows the wireless LAN modulation techniques, where you can see DSSS, and here you can see the data rate values of OFDM. DSSS reaches a maximum speed of up to 11 megabits per second, while OFDM can reach a speed of 86 megabits per second, where the OFDM 256 QAM 5/6 data rate is approximate. That's all I'm going to tell you in this lesson, so goodbye to see you in our next lesson.